Welcome back, students. Dr. DA here. We're going to continue our study of hydrocarbons. And in this lesson, we're going to go over other types of hydrocarbons, the cycloalkanes, the alkenes, and the alkynes. Starting with the cycloalkanes, as the word suggests, these compounds, which have the formula generically CnH2n, have a ring or cyclic structure. Remember that the carbon-carbon bond, you can rotate around it a lot. And since all of these carbons that are singly bonded have tetrahedral structures around them, you can envision where after a couple of carbons in the chain, you can twist it around and have one end of the chain actually covalently bonded to the other end. For example, in a 3-carbon compound cyclopropane, 3 carbons are joined together into this cyclic structure here. Notice that there are 2 hydrogens for every carbon. We can also draw this in the form of a skeletal structure, like a triangle. For a 4-carbon cycloalkane, we have cyclobutane. Again, as you can see, the carbons are connected to each other, forming a cyclic structure, which we could also represent with a skeletal structure of a square. Now, it's very important to remember that the bonding between these carbons is between sp3 hybridized carbons. So the structure is not really flat. It would have a bit of a twist to it if we could see the actual molecular shape. Next on our list would be cyclopentane. This would be a 5-carbon cyclic compound. And again, we can see the structural formula here on the left side, which we could narrow down to a skeletal structure. It looks like a pentagon. But once more, remember that these are not flat structures, although we represent them that way. The actual molecular shape would be a twisted pentagon here. Again, remember that each carbon will have 2 hydrogens connected to it, hence the CnH2n generic formula for all these compounds. The next in our sequence will be cyclohexane. This would be a 6-carbon cyclic compound that you can see there on the left. Again, to represent it as a skeletal structure, we can use a hexagon. And it's important once more to remember that these are not flat structures. As a matter of fact, cyclohexane can achieve 2 different kinds of conformations. One of them is shown here. It's what we call the chair conformation. And the reason we call it the chair is because, as you can see, 3 of the carbons would form kind of like the headrest. These 4 would form kind of like the seat of the chair. And then over here you'd have the footrest. And this is a very common structure, for example, in other compounds that have a 6-sided ring. For example, sugars like glucose and galactose. Now, in terms of nomenclature, we also have a set of rules similar to the ones that we had for regular alkanes. We're going to use the cyclic portion of the compound as the parent name. The substituents, again, are going to be listed in alphabetical order. And they're going to be assigned position numbers where necessary, but we're going to number the carbons on the ring so as to get the lowest possible sum of numbers. So let's look at this compound here. Notice that the parent here would be the hexagonal cyclic ring of cyclohexane. That is correct. And in order to have proper numbering, since these are next to each other, we would simply say that this is 1,2-dimethyl cyclohexane. Now, what if we have only one substituent? Well, in the cyclohexane molecule, really every carbon is equivalent. So for a single substituent, it doesn't really matter which carbon it is because we can just change the structure on just by spinning it, just by rotating it. And so we don't have to indicate a number for a single substituent. This would simply be methyl cyclohexane. Now let's look at this structure here where I'm just showing the skeletal structure. Again, be careful. We have a tendency sometimes to automatically think about the clock and say, well, this would be number 1, this would be number 2, this would be 3, 4, and this would be 5 over here. But we have to always consider other arrangements that give us a lower possible set of numbers. So let me erase these. And let's consider a different arrangement here. Let's call this carbon here on the top right, like at 2 o'clock. Let's say that is carbon number 1. And then let's go counterclockwise. That would mean this would be carbon number 2. And that means this one here would be carbon number 4 as we go around. That actually gives us a better set of numbers that add to a lower sum. And therefore, we're going to place these substituents in here. Now, notice that we have a 2-carbon substituent here, which would be ethyl. And then the other 2 substituents are single carbon attachments, which would be a methyl group. So alphabetically, ethyl would come before methyl, and we would call this compound 1-ethyl 2,4-dimethyl cyclohexane. Now it's interesting because the formula CnH2n can also be applied to another family of compounds called the alkenes. They also have the same formula, but the difference here is that these compounds have one or more carbon-carbon double bonds. So in this case, for example, we would not have a 1-carbon compound because you can't have a double bond if there's just 1 carbon. So our first item in the series would be C2H4, and we call this compound ethene. The next one, C3H6, would be called propene. Notice that it's similar to the nomenclature of the alkanes, except the ending here is ene instead of ane. When we draw these structures, many times we like to indicate the geometry around the carbon. We know that for a carbon with 2 single bonds and a double bond, you have sp2 hybridization, which produces a trigonal planar geometry. And so many times when we draw these structures, instead of making them linear, we actually go ahead and put the angles where the hydrogens are. So this would be ethene. Notice the carbon-carbon double bond. Propene could look like this, but remember that these molecules are not static, so we could have actually drawn this the other way and putting the CH3 group at the beginning. It's still the same compound. Again, notice the trigonal planar shape around the carbons that are involved in the double bond. Now, when we get to the formula for the alkene with 4 carbons, C4H8, we encounter an interesting situation. We could put the double bond between the first and second carbon in a chain, which we could also draw as a skeletal structure you see there in the bottom. And we call this compound 1-butene. In other words, we've had to indicate the position of the double bond. Why? Well, because we have another option. We could have placed the double bond between carbons 2 and 3. And in that case, we would generate 2-butene. But what's important here is to notice that because of the rigid nature of that double bond, you cannot rotate around it. And therefore, once you have set the positions of these carbons at positions 1 and 4, these 2 structures that we see here are not interconvertible. You cannot switch between one and the other by simply rotating around the carbon-carbon bond because that double bond is rigid. And so we have here an interesting phenomenon. These are called stereoisomers. They're called stereoisomers because unlike the structural isomers, for example, in this case, between 1-butene and 2-butene, where the position of the double bond is different, these two compounds, all of the connections between the atoms are the same. What is different is the orientation of the atoms in space, and that's what we call them, stereoisomers. In this case, if we come from the left side of the structure and we enter the double bond coming left to right, if we exit on the same side of the double bond to the next carbon, which would be carbon number 4, we call that the cis isomer. If, on the other hand, when we go through the double bond and the next carbon is on the other side of where we entered, we call that the trans isomer. This is an older nomenclature. When you take organic chemistry, you're going to be learning a more comprehensive way of naming these type of stereoisomers. But we will leave it at that. Just be aware that when you draw structures for atoms that have carbon-carbon double bonds, you may have to account for the possibility that there might be more than one stereoisomer in that case. Now, in terms of nomenclature, the rules that we follow are very similar to the ones we did for alkanes. We start out by identifying the longest continuous carbon-carbon chain, but the difference is that we have to include the double bond in that chain. So that means that the actual longest continuous carbon-carbon chain might not be the one that we use, because the one we use has to go through the double bond. We're going to use that as the parent name, but the termination is going to be ENE instead of ANE. Once more, we will number the carbons from one end, and the goal here is to give the double bond carbon the lower possible position number. So the position of the double bond is going to take precedence over anything else. Once we've set that up, we'll indicate the substituents and the position numbers as we did with alkanes. There is a possibility that alkenes can also go around and form cycloalkenes. In those cases, the position of the double bond will always be given number 1. Let's go ahead and apply these rules to some practice exercises. Here are 4 skeletal structures. Let's try to find the names of these compounds. Let's start with compound D. Remember, the first thing you want to do is you want to find out how many carbons are in the longest continuous chain that goes through the double bond. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. For 9, with a double bond, we're going to call our parent name nonene. Remember, regardless of where the substituents are, we have to allow the double bond to have the lowest possible position number. And therefore, if we start numbering the chain from this end, and that is carbon number 1, that means that the double bond is going to have a position at number 3. Let me fix that a little bit here. This will be position number 3. That means that our other substituent, which is a methyl group, will be at position number 7. Now, the other thing we had to look for is what is the geometry around that double bond. Notice that when you go from carbon 2 to carbon 3, you enter from, let's call it the bottom here. But when you exit at carbon 4, you're going on the other side. That means that we have a trans isomer in here. And so we're going to call this main parent 3-nonene, but it has a methyl group at position 7, and it has a trans type of stereoisomer around the double bond. So we're going to call this trans 7-methyl-3-nonene. Let's look at structure E. Again, let's begin by tracing the number of carbons, including where the double bond is. So we have 1, 2, hold on a second. Let me make sure I have my highlighter here. 1, 2, 3, 4, 5, 6, 7, 8. That means that our parent structure is octene. We have to make sure we give the double bond a specific number. So that's going to be at carbon number 1, which means that now our substituent is going to be at position number 6. Now, in this case, when we consider the possibility of stereoisomers, remember carbon number 1 is simply a carbon with 2 hydrogens and a double bond. So there is no interconversion that would generate a different stereoisomer. You can simply, spin the molecule around and you get the same thing. So there is no stereoisomerism in here. We will call this compound, therefore, 6-methyl-1-octene. Notice that we had to indicate where the double bond was. All right, let's look at example G. Once more, let's find what is the longest continuous chain. So it'll be 1, 2, 3, 4, 5, 6, 7. Which means that our parent compound would be heptene. And once more, we have to assign positions to our carbons. And we see that in this case, the double bond is at position number 2. Inspecting the way this molecule is arranged, we can see that once more, as before, when you go in from carbon 1 into carbon 2, let's say you're entering here from the top, but when you exit at carbon 3, you're exiting the chain at the other side. Right, let's do that in here again, which means that you have, again, what we call a trans isomer. Notice that your substituents now are going to be at other positions. They are going to be at positions 1, 2, 3, 4, and position 5 on the chain. So when we name this compound, we're going to indicate those positions. Again, remember, the double bond takes precedence. So this would then be trans 4,5 dimethyl 2-heptene. Let's look at compound H here. Once more, start out by establishing what is the longest continuous chain, but don't forget, it has to include the double bond. So we're actually going to be starting up here. 1, 2, 3, 4, 5, 6. Notice that that chain would give us a parent hexene, and in this case, the double bond will take position number 1 up there. That means that these other 3 substituents are going to be considered as methyl substituents. And we are going to have to count all 3 of them at positions 2, 3, and 4 on the chain. Is there stereoisomer possibilities here? Well, no. The carbon at carbon number 1 has 2 hydrogens. In other words, the 2 groups attached to it are the same, which means that there is no need to twist around that bond, break that bond and twist it in order to generate the other version of it. So there is no stereoisomer here. So we're going to call this compound 2, 3, 4 trimethyl 1-hexene. The other set of hydrocarbons are the alkynes. These have the generic formula, CnH2n-2, and we distinguish them because they'll have one or more carbon-carbon triple bonds. In other words, there will be a linear geometry around that triple bond. Nomenclature is the same rules as alkenes. The only difference is that the ending now is Y and E. So for example, the 2-carbon compound will be ethyne, the 3-carbon compound propyne, and so forth, with the provision that you may have to indicate the position of the triple bond where there are isomers possible where the triple bond is at different positions. Now there are some extras here that I want you to take into account. You will be reading this mainly on your own. Everything that we've talked about so far involved the positioning of alkyl substituents, methyl, ethyl, propyl, etc. But there are other substituents you can put in that are non-carbon. For example, you can put halogen atoms like chlorine or bromine. In that case, you will call those substituents the chloro or bromo substituent. Also, the NO2 serves as a substituent, and we call that the nitro group. There is another large category of compounds called the aromatic compounds. For lack of time, we're not going to discuss them here, so I encourage you to go to your Top Hat text where we have included the OpenStax chapter on organic chemistry, and you can read about aromatic compounds in section 20.1. Thank you so much. It's been a pleasure being with you. In our next lecture video, we're going to talk about other families of organic compounds that are not hydrocarbons, and also some of the important chemical reactions that we study with organic compounds. Thank you so much.